Yeah, welcome, Damon. So we're just getting rolling here, and as I was looking over the entire this gigantic 3.4 lesson, there's one part of the lesson that I don't think either. I don't know. It didn't seem to me it was presented clearly, and so I don't have any words here yet, but I'm going to give them to you in a minute. And that is what happens when you need to take the derivative of an exponential function. And that's with any base a. So you notice at the top of the screen here, f of x equals a to the x, where a could be, you name it, any base. And the answer is the derivative is, just like with e to the x, it starts off with the derivative is itself, and that would be this part. The derivative is itself times the natural log of its base. So in this case, the base of the exponential number was a, so you have to multiply by the natural log of that base a. So the derivative of any exponential function is itself multiplied by the natural log of its base. Okay, now that gives you what? Maybe new insight into that one of those first derivatives I knew, which was what happens when you want to take the derivative of e to the x? Actually, it's itself times the natural log of its base. And the natural log of e is 1. And that's why the derivative of e to the x is itself. So, I mean, e to the x works out special because the natural log of that base is always 1. And so then it makes the derivative much simpler. But looking at it from this wider view up on the top, now we can take the derivative of any exponential number. And there's an example in the book that shows this. Look at the very first example there, a. If you want to take the derivative of a function like 2 to the x, except they wrote it in the opposite order, it's itself times the natural log of its base. I mean, they have the multiplication the other way, but so anyway, there's a quick example of that. So what happens when you have a little more complicated one, like in part B there? What if you want to take the derivative of 2 to the 3x? Well, once again, it's itself times the natural log of its base. And then here we have a chain rule because the exponent itself is a function, 3x. And so we have to, we got to include the chain rule and multiply by 3 also. So anyway, I after going through all the stuff we went through, somehow I didn't feel that was presented to you in all those crazy rules, and maybe it's still coming in a subsequent lesson, but I felt I needed to get that in there. So just one more time, if there's new material today, it's this. In order to take the derivative of an exponential function, that's any constant to the x power, the answer is itself times the natural log of its base. So you need to add that to your list of derivative rules. And that reminds me, at the very end of the lesson, the book does present this. And I would say this is a really nice reference, okay? I don't have the page handy, but toward the end of lesson 3-4, you'll see you've got all the derivative rules thus far. And this, I think this is really important for you guys to have as a reference and to have as a study tool. So, I mean, quickly going over the easy ones way at the top. The derivative of a constant is always 0. Then we had the wonderful simple power rule. You know, just multiply by the power and reduce the power by 1. The constant multiple rule, which said ignore the constant and just take the derivative of the rest and then slap the constant back on again. I mean, the sum or difference, which we don't even have to remember because it works just like you want it to. If you want to take the derivative of a sum, you can take the individual derivatives and add them up. So the derivative of a sum is the sum of its derivatives, just like you want it. And difference too. And then we learned in this lesson the product rule and the quotient rule, which I don't know, hopefully you can get their notation there. And then, really important, I guess, by the way, I guess these were from the previous lesson. And then the chain rule, huge, probably the main rule in lesson 3.4. And that created this general power rule, which is just the power rule with the chain rule kind of tacked onto it. And then we have our what? Our 6 trig function derivatives right here. And then, yeah, here's the one I just showed you. The derivative of an exponential function, a to the x. Again, they wrote it the other way, but it's the same thing. It's itself times the natural log of its base. And then this natural log thing. Okay, so what's the derivative of the log of x? And the log can be any base a. And that is 1 over x. And in the denominator, also multiply by the natural log of its base. So, I mean, I would prefer to write that like this. But it's the same thing. So, okay, so yeah, this was kind of the easy version. It's always easier when you do the natural log. Well, the one on the bottom handles the log to any base. Just like over here on the left, this is the easy version of an exponential function, the e to the x, and on the bottom to any base. So there's a summary of the derivatives so far. So then I thought what we'd do is, I mean, these are some of the problems from the, what do they call those, the core exercises, and I thought we'd start, I picked out some, I want to do a bunch of examples. Basically, that's what I thought we could do today. And you guys are probably already starting and digging in on these. So I picked out some to get started on. And the first one I picked is number 17. Excuse me. Nice that we have a recording of me blowing my nose. My apologies. Okay, so number 17, here's the function. And we want to find the derivative. You know, I'd write this with f of x, but so, you know, what is y prime? I want to change to blue here or something else. Let me get my keyboard off of here so I can write a little bit better. So this has got to be the quotient rule, right? So the denominator times the derivative of the numerator, which is, I mean, the numerator is a constant, so that's going to be a 0, minus the numerator times the derivative of the denominator. Well, easy derivative in the denominator, all over the denominator squared. So, I mean, what's left on top here? Just a -1. So that's pretty easy. Pretty easy application of the quotient rule. I'm always going to pause just for a few seconds in case somebody has a comment or a question. So there's one example, number 17. By the way, I kind of mixed it up between odds and evens, so some of these you may have already worked on. I'm going to go to 23 now. So 23 is pretty obviously going to have to be I mean, I suppose we could take x minus 2 times x minus 2 times x minus 2 times x minus 2 and then multiply all of that by x squared and then do an old style derivative. But in order to practice the product rule, I'm going to do it that way. Switch my power cord around a little bit here. Crimped. Okay. So the product rule says that f prime of x would be what? The first times the derivative of the second. And the second is what? X minus 2 to the fourth. So we got to do what? First of all, the power rule. 4 times x minus 2 to the third. Actually, a chain rule there, but, you know, the derivative of x minus 2 is 1, so we could have skipped that. Good habit not to. Plus the second times the derivative of the first. As is always the case, it seems like sometimes the simplification is more of an issue than the derivative. So anyway, let's keep going here. So this is 4x squared times x minus 2 cubed. And I'm going to put the 2x in the front times 2x times x minus 2 to the fourth. As they say in the book, we could maybe do some factoring here. So you notice that there's 2 terms here. 1, 2, and in each term we have an x minus 2 to a power and we have an x expression. So we could out what? Maybe a 2x that divides into both 4x squared and 2x. And we could take out an x minus 2. What's the lowest power? To the third power. And that would leave us with, in the first term, what? Just a 2x. And in the second term, the 2x is gone, and all we have is an x minus 2 to the first power. So I'll just write it like that. Well, what happens if we simplify what's in brackets? It's just 3x minus 2. So I would say that would be a good place to leave it. You sure don't want to multiply that out. In my opinion, I would be happy with that ending point. Again, anybody have a comment or a question about number 23? So you probably notice I'm going kind of in a, we're kind of climbing the ladder. We're getting a little bit longer. And this next one is a good example of that. I want to go to number 30. So we want to take this quotient that's squared, okay, and we want to find its derivative. So, what I did is I went ahead and squared it. So this now becomes, so here's a case where I'm doing a little bit of algebra before I begin. And here I'm just going to call this t cubed plus 2 squared. Now, maybe, let's do the derivative. So h prime of t. And now we got to use the quotient rule. Okay, quotient rule. So, denominator times derivative of numerator minus numerator times derivative of denominator. Now, the derivative of denominator I got to look at it from the outer point of view first, which is, power rule. And then, is there an inner function? Oh, yes. There's a t cubed plus 2, so I have to multiply that by 3t squared. And then, of course, all over denominator squared. So, it gets a bit messy. Let's just rewrite the top a little bit. We've got, I'm going to put the, I'll leave the quantities squared toward the end. It doesn't matter, but I'm going to just write it like this. Bring the 4t cubed out to the front. And then likewise on the other side. Now here I can combine what? 3t squared times 2 times negative t to the 4th. I can multiply all of those. And that would give me what? Negative 6t to the 6th. And then I still have the t cubed plus 2 in there. And all of that's over t cubed plus 2 quantity squared. And hopefully you can see there's this t cubed plus 2 theme. And if we do some factoring, so on the top, what can we factor out of those two big terms? Well, we could take out a what? A 2t cubed. And we could take out a t cubed plus 2. Take out the 1 to the lowest power, which is a 1. So what does that leave us left on the top? When you take out a 2t cubed out of that first one, you're going to have 2. And you're going to have a t cubed plus 2 to the first power. And then on the second part, what's left? Well, it'd be a minus 3t cubed. And that's it. Okay, so now we can do some canceling, can't we? Oh, you know what? I forgot to square the denominator, didn't I? Yeah. Sorry, I just realized it's over the denominator squared, and it was already squared, so those should be 4s. Everybody, so over denominator squared, and it already was squared. I was supposed to square it. Okay, so now can we do some canceling? Yeah, we can cancel this t cubed plus 2 on the top with one of the 4 on the bottom. And then what does this turn out to be here? This just turns out to be 2t cubed plus 4 minus 3t cubed. 2t cubed minus 3t cubed is 1t cubed. So on the top, we wind up with, after we cancel this with one of these, on the top we wind up with t cubed times negative t cubed plus 4. That's not very clear. Wow. Okay, times that all over t cubed plus 2 to the third. And I'm going to just do a little multiplying here. Negative 2t to the 6th plus 8t cubed. I mean, that's about as far as I would go. It certainly would not multiply out that cube on the bottom. I would stop there. Okay, so that one's kind of lengthy, but pretty much what? A straight on quotient rule. Okay. See, I'll just hang on a second because there's a lot of stuff there. Any other comment or question there? I thought next we're changing, let's take number 50, where we get into trig functions. Now, half the problem with trig functions is the notation. So what does it mean when it says h of x equals secant x squared? That doesn't mean the same as secant squared x. So what this, maybe to make it clearer, doesn't it mean this? So the outer function here really is the secant, and then the inner function is the x squared. So you need to remember, how do you take the derivative of secant? And you remember it was secant. So what's the derivative of secant x? It was secant x times tangent x. So when we take the derivative, so first of all, it's secant x squared times tangent x squared. So that's just following the derivative. And now, is there an inner function? Yeah. So we still have to multiply by the derivative of x squared. And there really isn't anything, I wouldn't simplify this. I'd just leave it like this. I mean, you can put the 2x in the front, but. So here's a case where it's more of a notation issue than anything. Be careful with trig. Where really are the parentheses? Because we pull these new rules where we say secant squared means really that's an outer function. So I got a couple more I'd like to do with trig. Let's take a look at number 60 next. So here's one of those, this is what I was talking about. Cosine squared of 8 theta. Cosine squared of 8 theta. Doesn't that really mean the cosine of 8 theta squared? I mean, that's what that notation means. And unless you see it that way, you can't see what the outer function is. And hopefully now you can see that the outer function is the squaring. So in other words, when we're going to take a derivative, we got to do the power rule first. Okay, so when we take g prime of theta, we first do the power rule. Bring the exponent down, keep the rest of it the same to the first power, so I don't have to write that. Okay, now do we have an inner function? Oh yeah, we got a bunch of things going on here. So the next thing as you're going toward the inside is we need to do the cosine. What's the derivative of the cosine? That would be what? Minus the sine. So we got to multiply by minus the sine of 8 theta. And are we done? Actually, no, there's even another inner function, and that is 8 theta. And the derivative of 8 theta is 8. So here's a case where we have, what, 2 functions nested? And here's where you got to keep your antenna out for that chain rule. That chain rule is so important. And then, of course, you could bring this together and just say, we got a negative in there, so it'd be negative 16 cosine 8 theta sine 8 theta. And I would leave it, I would say then that one is complete. So here's a good reminder of the chain rule. Watch out for that nesting. Otherwise, you won't be able, you obviously won't finish your derivative. So anybody question or comment from there on there? You know, I'm just going to go back. I'm just checking on the pictures here. So we have Damon, we have John, we have David, we have Caitlin, and we have Geneva. Welcome. If I haven't said it, welcome to all of you. Glad to have you. A little bit surprised that only that many are going live, but anyway. Anybody question? Otherwise, I'm going to go to number 68 for my next one. Number 68. So another trig. You talk about nesting. This is what? Almost like nesting heaven here. Okay, we got nesting going on like crazy. So the first thing I'm gonna change this to f of x. So f of x equals the cosine of, and really it's of this whole thing, right? This is not multiplication here. This is just a situation of, you know, it's the cosine of all of that stuff. Okay, so I'm going to just write it like that. I should have made this longer. Whoops. I should have made this longer. So now we've got the sine of the tangent of pi x. So like I said, this is kind of like nesting heaven here. So could I not think of this as the cosine of the sine of the tangent of pi x to the 1/2 power? So just rewriting the square root. Okay. Now, what's really important here is what's the outermost thing going on here? It's the cosine. So the first thing I got to do is I got to say, if I'm going to take the derivative, I've got to handle how do I take the derivative of the cosine? And that would be minus the sine of all the same stuff. So that's the beginning. Now, as you move in, what's the next most inner thing? Now it's the power, right? And I know it's a little difficult to see here, but the next thing is that all of that to the 1/2 power. So the next thing I have to do is do the power rule. So as I'm doing the chain rule, I have to take the power down in front, and the rest of this stays the same. Reduce the power by 1. Just trying to make sure I have parentheses in the right place here. Okay, so I reduce the power by 1. So there's the power rule. Now, what's the next thing going on inside? As I move inside those parentheses, the next thing is what? The sine. It's this sign now. And what's the derivative of the sine? It's the cosine of the tangent of pi x. All right. What's the next thing on inside? Oh, it's the tangent. And what's, I don't have enough space here, so I'm going to have to just continue here. So what's the derivative of the cosine? minus the sine, right? So times minus the sine of the tangent of pi x. Okay, and now as we go inside that, what's the next thing going on? The tangent. And what's the derivative of the tangent?
Why did we take the derivative of the cosine there? I thought that was the derivative of the sine.
Yeah, let me think. What did I do there? Minus 1/2 the sine. So I did the power rule. Say that again. You thought that was the derivative of what?
I thought the cosine was the derivative of the sine.
Oh, you're right. I shouldn't have put that in there. Thank you. So the next thing is the tangent, right? As we move inward, tangent. And what's the derivative of the tangent? Secant squared of pi x. And finally, what's the last thing that's in is that pi x. And what's the derivative of pi x? Pi is a constant, so that would be times pi. I mean, that is one colossal chain rule there. And I'm not even, we're not going to attempt to simplify that. But, I mean, I suppose that could be done. But it was more important that we just see all of that put together. Yeah, thanks for that comment. Okay, let's, the next one I found was number 72. So now we're going to get into, what do we do with these exponential guys? Okay, and overall, this has got to be a product rule, right? We got x squared times e to the negative x. So we need to do, so let's just first rewrite this with a f of x equals x squared times e to the minus x. So the product rule says take the first times the derivative of the second. Okay, now think carefully. What's the derivative of e to the negative x? Well, it's itself. But there is an inner function, and that is negative x. And the derivative of negative 1x is negative 1. So we do have, there's the chain rule, plus the second times the derivative of the first. Okay, now, I mean, there's different ways to do this, but I would rewrite this way. So this first term is negative, and e to the negative x is really the same as what? E to the x in the denominator. Same thing over here, e to the negative x. And so we could just bring this together over the common denominator. And I would say that would be a good place to finish that one up. All right, how about number 86? 86. I'm trying to select different types to at least get us warmed up at least to some of the different possible things we have to do here. So here we have a natural log problem. Do you remember what the derivative of a natural log is? We just had that recently in this lesson too. That was what, 1 over that thing? So what's the derivative of the natural log of x? 1 over x. And that's the outer function here, right? So as we do h prime of x, we have to first think of the outer function. And so that would be 1 over that whole thing we were taking the natural log of. And of course, do we have an inner function? Certainly we do. the inner function is 2x squared plus 3. And so as we do the chain rule, the derivative of that is what, 4x? So I guess more important than anything, just that you realize how the chain rule looks in some of these different situations. So that one's pretty straightforward. But there's an example of how you have to carry out the chain rule in taking the derivative of a natural log. All right, I also marked down number 93. So you can see I'm still trying to include some odds here. So 93, g of t equals the net log of t divided by t squared. So from an outer function point of view, we have what? A quotient. So we need to use the quotient rule. So g prime of t, and we go through our quotient rule. Denominator times derivative of numerator. What's the derivative of the natural log of t? 1 over t. So denominator times derivative of numerator minus numerator times derivative of denominator. And then, of course, that's over the denominator squared. Okay, simplify a little bit. Well, what's this t squared times 1 over t? That's just t, right? So we have t minus, I'm going to put the 2t in the front, 2t times 2. Okay, having a little technical difficulty here. 2t times the natural log of t. There we go. And that's all over t to the 4th. Can we factor a t out of the top? Sure. T times the quantity, 1 minus 2 times the natural log of t. And then, of course, we could cancel. And we'd have 1 minus 2 times the natural log of t. T cubed. All right. So that's my quick look at some examples. Now, some of you have started. I probably have. I encouraged you to dig into your assignments. Do you want to ask some questions? Pick out any you worked on, or you want to pick out another problem or two. We have about 10 minutes we could still use. So finally, this mammoth, I think, this is a huge lesson. There's so many different it's like, I don't know, it's like they took 5 lessons and put them together, almost. Oh, 129 from Damon. Got it, Damon. Let's see if I can go find that. So do I have that up here? Let me just take a look. I don't. All right, so let's go. Actually, I'll find it in the book. Try to. Second derivative. Okay, so let me just quickly grab this. And then need my keyboard again. Okay, and then let's come down here and we'll paste it in. Well, I barely got that. All right, so, oh, I missed. Okay, that wasn't so good. So let me go back and look at what was 129. Sine of x squared. All right, sine of x squared. So 129 f of x equals the sine of x squared. And you know that means this, Damon. So first of all, if we're going to take the derivative, we know that the derivative of the sine is the cosine. So that would be the cosine of x squared. Okay, and then we need to do the chain rule. And that should be the first derivative, which we could probably rewrite as 2x times the cosine of x squared. So then if we're going to do the second derivative, we have to take the derivative of this thing. We'd have to use the product rule. The first times the derivative of the second. Well, the derivative of the cosine of something is minus the sine of that. And then we have to take the chain rule. Okay, so first times derivative of second plus second times derivative of first. So I guess it's just a matter of how are we going to end this up now. So I don't know. Let's see what we got. We certainly could factor, yeah. Well, let's just rewrite this. Okay, so this first one is 2x times 2x is 4x squared times negative the sine of x squared. And the second one, 2 times the cosine of x squared. And I don't know, is there anything we can really do with that? I think I'd just leave it like that, Damon. I mean, you know what I maybe should have done is I could have taken this negative sign here. Probably a little neater is take this negative sign and stick it out in front. That's about the only thing I can think of that would put it in a better format. David asks for number 91. All right. So let's go back and grab 91. This time I'll try to actually grab it. Okay, number 91. Keyboard back again. Okay, number 91. I think that one is on my list here. Here we go. So let's snapshot that. Okay. So number 91. So we're supposed to take the derivative. I didn't bring the directions, but I'm assuming that's what it is. How do you take the derivative of a natural log? It's supposed to be 1 over that thing, right? Well, what's 1 over a fraction? Isn't it just that fraction reciprocated? So that would be 1 over x squared plus 1, which is x squared plus 1 over x. Now, what's the inner function? Well, it's a quotient. So now we have to, as we do the chain rule, we have to execute the quotient rule. Okay, so denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. So,
Is that top part for your quotient rule the right way? Because wouldn't it be 2x times x?
isn't that what I have right here?
Wouldn't that be in the front part though? Like, wouldn't that
Oh,
be?
yeah. You always want to take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. So no, it has to be that way.
Wait. Didn't you just say the denominator times the derivative of the numerator?
Yeah, isn't that what we have right here?
Oh, okay. I
Denominator.
thought you don't use the reorganized function like the x
No,
squared.
you use the original inner function.
Oh, okay. Never mind.
So I need to be looking up here when we're talking denominator and numerator.
Okay, so whenever you're doing the chain rule, it always goes back to the main equation.
Always go back to the original inner function. Yeah.
Okay, that makes
Yeah,
sense.
so I'm kind of glad you asked about this because you're right. That could be confusing. Everybody get that? So what David is saying is when you use the quotient rule, which is the denominator, which is the numerator? It's of the original quotient. So I gotta look back like where the red arrow is. I gotta look back. Yeah, don't use the reciprocal. I mean that's a different thing. That's the derivative part. Okay. So let's see. I just got to erase this. So as we continue here, I don't know. Well, wrong color, but whatever. And then over on the top here, what do we have? Minus 3. So it's x squared minus 3x squared. Right? Because this is 2x squared and x squared minus 2. Hang on. What did I do? X squared minus 2x squared. That should be minus x squared, shouldn't it? Okay. Now I just write it out instead of trying to do this. So it's x squared plus 1 minus 2x squared all over x squared plus 1 squared. X squared plus 1 over x. Whoa. Over x times, and then this would be 1 minus x squared all over x squared plus 1 squared. And now I can certainly cancel this and one of these. And then what I'd have left is what? 1 minus x squared over x times x squared plus 1, which of course x squared plus 1, what? Why did I write? Oh, that's a squared. Yeah. So on the bottom here, x squared plus 1. You can multiply it out, but I would say leave it like that. Okay. So those are the two I got from you guys. Let's see, we're at the 50-minute mark. I think we're going to call it quits. Thank you for the good questions. Thank you for your attention. So we got this bigger assignment now. Finally, should have it ready to go. And I will see you on tomorrow. Thanks, everybody.